This is running live right now, so it can detect the number of persons. So right now I am alone in my room right now, so it is detecting only one single person. This is the interface. So right now your Wi-Fi router is sending signals straight through your body. Not tomorrow, not when you open an app. Right now. Every second those radio waves passes through your walls, bounces off your furniture, bounces off you. Every movement you make, every breath you take, changes those signals. And over years, your router has been measuring all of it, only to throw it away. Now imagine this. What if, instead of throwing that information away, you could actually use it? No cameras, no smartwatch, no wearable, just Wi-Fi. This tiny board costs less than $10, yet it can detect someone's in the next room, estimate how many people are inside a house, measure breathing, detect falls, and in some cases, even estimate heart rate. That sounds impossible, right? I thought so too. So this week, I built one, and honestly, I didn't expect it to work as well as it did. This project is called RuView. It's completely open source, and in the next few minutes, I'm going to show you exactly how it works and build a working sensor using an ESP-32S3, and I'll show you the upgraded version that completely changes what this thing can do. Because one sensor is actually less interesting part. The real magic happens when you connect multiple sensors together. That's when it stops acting like a motion detector and starts understanding an entire room or even an entire floor. Let's build it. Wi-Fi doesn't send information on one single frequency. It splits the signal into dozens of tiny subcarriers. Imagine 56 tiny microphones all listening to the same room from slightly different positions. Every packet tells the chip how each subcarrier is changed. The collection of measurements is called raw CSI data. An empty room produces a stable pattern. A moving person disturbs it. Breathing creates a slow rhythm. Heartbeat creates a much smaller, faster rhythm. RuView filters the raw signal, removes the noise, then looks for the repeating patterns. Finally, a lightweight neural network running directly on ESP-32 devices, whether someone is present, whether they are moving, breathing, or may have fallen. The remarkable part isn't just the AI. It's all this starts with an ordinary Wi-Fi signals that were already there. Alright, so what did I actually build? Turns out, it's surprisingly simple. The entire project runs on one board. This tiny little thing right here is an ESP32S3, specifically the N16R8 version. Those numbers actually mean something. It comes with 16 megabytes of flash and 8 megabytes of PS RAM. That extra memory is important because this board isn't just collecting Wi-Fi data. It's also buffering that data, running filters, and even running a tiny AI model on the device itself. No cloud, no server, no GPU. Everything happens right here. And the best part, the board costs around $9. Step 1. The ESP32 starts listening to nearby Wi-Fi traffic. It captures something called raw CSI data. Remember, that's the hidden information we talked about earlier. The really cool part, it doesn't need internet access. It isn't uploading anything. Everything runs locally, right on the chip. Step 2. The board throws away bad readings. Wi-Fi is noisy. Another device joining the network creates random interference. All of that create garbage data. So before doing anything else, the firmware filters out the unstable measurements. Think of it like cleaning a dirty camera lens before taking a picture. Step 3. Now comes the signal processing. The clean CSI data goes through several filters, designed to remove spikes, reduce echoes, and isolate the useful patterns. This is where breathing signals start speaking for itself. All the background noise without this step, the AI would be making decisions based on junk. Then comes my favorite part, the neural network. And honestly, this surprised me. The entire AI model is only 8 kilobytes, not 8 megabytes, 8 kilobytes. That's smaller than many icons on your phone. Yet, it's capable of recognizing whether someone is present, whether they are breathing, and even detect falls. The entire model runs directly on ESP32. No Raspberry Pi, no external computer, just this tiny board. Once the model finishes its prediction, the firmware packages everything into its own format called RVF. Flashing is very simple. You connect the board over USB, run ESP tool within a few seconds, it's ready to go. So, what one node can actually do? Forget the marketing videos. Here's what genuinely actually works. It can reliably detect whether a room is occupied, estimate how many people are inside, track breathing, detect falls, and respond to a fall in under 200 milliseconds. That's incredibly fast. Even better, all of those readings are published over MQT. If you're using an home assistant, it just appears like any other smart home sensor, presence, breathing, occupancy, all updating in real time. And that's the best part. I wanted to verify myself. Not in a research paper, not in a demo video, on my own desk, with my own hardware. And after testing it, I can confidently say this part actually works. Alright, before we go any further, I want to be completely honest with you because YouTube comments are ruthless. And if I don't say this, someone definitely will. You have probably seen videos of research papers showing Wi-Fi tracking a full human skeleton. Every joint, every arm movement, every leg. It looks incredible, but here's the catch. Those systems aren't using a tiny $9 ESP32. They're using expensive research hardware, multiple antennas, high-end network cards, powerful computers, and a lot more processing power than this board. This board just only has one antenna and 56 Wi-Fi subcarriers to work with. That's enough to do some really impressive things, but it also has limits technically. This project can estimate a 17-point body skeleton, but the developers themselves describe it as a first-cut implementation. In other words, experimental. It's rough, and honestly, it's nowhere near the polished demos might have seen online. So, I'm not going to fake one for a thumbnail. I'm not going to smooth it out with an animation or pretend it's more accurate than it really is, because that's not the interesting part anyway. With what one node actually does well is the practical stuff. It knows whether someone is in the room, roughly how many people are there, whether they're breathing, whether someone has fallen. Those features, they already work really well. But here's the problem: one sensor only sees the world from one point of view. It knows something changed. It doesn't know where. And that's exactly this project gets really interesting. Because the solution isn't a bigger sensor, it's more sensor. So, why can one sensor track someone moving through a room? It comes down to perspective. Imagine standing in the corner of a room with your eyes closed. You hear a sound. You know something's happened, but you can't tell exactly where it came from. Probably not. Now imagine someone standing in the another corner of the room. Compare what both of you heard, and suddenly finding the exact location becomes much easier. That's exactly what's happening here. One sensor has only one point of view. It knows something changed. It just doesn't know where. So instead of making one sensor smarter, the project does something much more clever. It gives friends. Upgrade number 1. Frequency diversity. Normally, a Wi-Fi device stays on the channel. It listens, it talks, and that's it. But these nodes do something different. Instead of sitting on a one channel, they hop across multiple Wi-Fi channels on a carefully timed schedule. Each channel gives us 56 subcarriers. Well, if you combine data from these 3 channels, you suddenly have 168 virtual subcarriers. Same hardware, same cheap 32 EST. Think of it like upgrading from a blurry photo to a much sharper one. The information you have, the easier it becomes to tell exactly where a reflection comes from. Upgrade number 2. This is where things get really clever. Multiple viewpoints, or what researchers call multistatic vision. Here's an easy way to picture it. Imagine shining a flashlight across a room. You'll see some shadow. Now imagine 4 flashlights, all pointing from different directions. Suddenly, those shadows become much easier to understand. That's exactly what Mesh is doing. Every node can hear signals from every other node. So when someone walks across the room, they don't disturb one signal. They disturb dozens of wireless paths at all the same time. Instead of asking, did something move? The system starts asking, which links changed? Which direction? Where did those changes overlap? Once you combine all of those answers, you don't just know that someone is there. You know where they are and where they are moving. That's a massive leap. One node says someone's here, 4 nodes says someone's here and walking towards the kitchen. Upgrade number 3. Timing. Imagine trying to record a concert with 4 cameras. If every camera starts recording at a different time, good luck syncing that footage later. The same thing applies here. Every sensor has to agree. One exactly where captures its data, that exactly why the nodes synchronize using ESP-NOW. It's a lightweight peer-to-peer wireless protocol, no cloud, no internet, no router in the middle, just direct communication between the nodes. The project reports over 99% synchronization, which means all of those measurements line up almost perfectly in time. Without that, the mesh simply wouldn't work. And here's the really exciting part. It scales. One access point can comfortably monitor around 3 to 5 people, and more nodes, more the coverage grows. In large spaces, a 4-node mesh can cover roughly 15 to 20 people without adding expensive hardware, without installing cameras, just more of the same inexpensive boards. Think about what that actually means. We have gone from a single occupancy sensor to something that completely understands how people move through an entire space. Not just someone walked into the room, but someone entered through the door, walked across the room, using nothing more than Wi-Fi signals. And honestly, that's the moment this project stopped feeling like a clever experiment and started to feel like a glimpse of where ambient sensing is heading. Alright, enough talking. Let's see it in the real world. This is my setup. I've got only one ESP32 node just mounted around the room. Nothing fancy, just an inexpensive board. The entire setup is only this one single board I have right now. Now watch the dashboard. I'm not wearing a smartwatch. I'm not carrying a tracker. There is no camera following me. Everything you are about to see comes from ordinary Wi-Fi signals. That's it. I'm going to walk into the next room. Keep your eyes on the dashboard. There. Did you catch that? The occupancy changed almost instantly. The presence sensor updated, the room count changed, and the mesh knew exactly where I moved.
All of that happened without a camera, without infrared sensors, without GPS, without Bluetooth beacons.
See my live screen. This is running live right now. So it can detect the number of persons. So right now I am alone in my room right now. So it is detecting only one single person. This is the interface. So these are the skeletons. So normally if you have a mesh connected using multiple ESP-32 sensors, so it can detect even the skeleton movements and the body pose, the person is standing or the person is sitting or the person is exercising, etc. So as you can see, it's running on auto cycle mode right now. So it has many modes. So it has vital signs. So as you can see, this is my heart rate and respiration rate. So this is the confidence score of the AI model that is predicting the heart rate and the respiration rate. I think it's okay. I don't know how to check this. So we'll just focus on the tech part. So it has got sleep monitor and it has got multi-person. So and the next one, fusion, fall detection, flood mode, search rescue, elderly care, fitness, security patrol. This product can be upgraded into many ways. Let me know what you guys think about.
Just using radio waves, and that's the best part. That completely changed how I think about Wi-Fi. We always thought of it as something as that connects device, but also a sensor. It's constantly interacting with the world around it. Walls, furniture, people, even your breathing. Most routers simply ignore that information. This project finally gives us a way to use it. And honestly, seeing it work on my desk, one of those moments where you realize the future is already here. Most of us just haven't noticed it yet. So, that's RuView, a completely open source project that turns something almost every home has into a surprisingly powerful sensor. If you want to build one yourself, I have linked the GitHub repository and along with my exact part list down in the description. So you can follow along or improve what I have done. Now I have a couple of ideas where to take this next. I could expand it into a multi-room tracking system or explore fall detection and whether see it could become a practical safety for elderly people. Both are really interesting projects. So let me know which one you would like to see one first. I'll build the one you vote for the most. And what's exciting about this project isn't just what it can do today. It can tell us where the technology is heading, ambient sensing, privacy first detection, smart homes without filling every room with cameras. We're still at the beginning. The hardware is inexpensive. The software is improving incredibly. And because it's open source, anyone can contribute. If you enjoyed this deep dive or learn something new today, consider subscribing. I've got a lot more projects like this coming, from AI to embedded systems to cybersecurity, and the kind of technology that usually stays hidden behind a research paper. So if that's your thing, you're in the right place. Thanks for watching, and I'll see you in the next one.